See you then. All right. So I'm going to work through question 1 as a worked example. So the first step here is if you can find the current through the whole circuit first, then you should absolutely do that. So A1 is just the total current because it's the current going into the battery, right? So A1 is going to be the total current. So this is going to be I total. And just using Ohm's law, that means it's V total over R total, which means it's 40 volts over, and because these are in series with one another, that's just 40 volts over 1,000, so it's going to be 0.04 amps. Okay. The V is a little bit more difficult because we're only looking before and after a single resistor, not over the whole circuit. So we're not going to get that full 40 volts. We're only going to get some fraction of that 40 because each electron or each bit of charge, each bit of current goes through here, drops some of its 40 in there and some of its 40 in here. So we're going to work out what that is. We use V equals IR this time, but we use it at the level of the actual resistor itself. And so the I going through that resistor, well, because it's all in series, it's just the same I that's going through the whole circuit. So that's 0.04 amps. And the R is now only that 600 ohms because we're only concerned with that one resistor. So the total there is going to be, multiply those two together, you get 24 volts. Okay, so hopefully a straightforward series circuit we're okay with. Things get a little bit more complicated when you get to the circuit 2 here. And I'm actually going to redraw this circuit using our redraw method. Oh, that's not paper. Oh, yes, it is. Hold on. There we go. Using our redraw method. So I'm going to take this circuit here and I'm just going to redraw it in a slightly more simple way. So here's my battery. And first off, I'm just going to take anything that's in series with one another in a clean way and just turn that into one resistor, one effective resistor. So I'm going to take those two there and call that a 1,000 ohm resistor. And nothing's happening over on the other side at the moment. So it's something like that, and this is 36 volts on there. Right, and where am I trying to find? I better make a note of what I'm trying to find. I'm trying to get this current in here, and I'm also trying to get the current here. And then I'm going to come back to my original diagram to get that voltage because it's internal to one of the changes I've made here. Okay, well, I want to take these two now and I want to find the effective resistance of those two together. So what I'm going to do is I'm going to redraw again. Now, this redrawing process may be literal redrawing or it may be sort of mental redrawing, but either way, you're doing some redrawing. And what we've got here is some effective resistance that I don't know exactly what it is yet, but I know it's the parallel version of these two resistors here. So I'm going to use my parallel rule. So R effective is going to be 1 over 800 ohms plus 1 over 1,000 ohms. So that's, I'm going to pull out a factor of 200. So 1 over 200 ohms equals a quarter plus a fifth. So 1 over. So 1 over 200 ohms equals 4 20ths plus 5 20ths. So that's 9 20ths equals 1 over RF. So RF is going to be 200 times 4/9 is equal to 444.4, however many fours you want to do, ohms. Okay, so that's our effective resistance. And notice that this ammeter here is actually now somewhere inside that resistor. So we can't deal with that yet, but we can find this, what are we calling it here? We called it A1. we can find this A1 which sits outside of everything. And that A1 is going to just be the total current through the whole circuit. So it's going to be 36 volts divided by this total resistance, 444.4 ohms. So A1 is going to be 36 volts divided by 444.4 ohms. And that comes out to, I've got it written down over here, 0.081 amps. Okay, so we've got 0.081 amps, but then we need to sort of, okay, we've got that, yeah, all right, we got that total. But now we sort of need to work our way backwards back into the circuit to see what those internal ones are. So this is 0.081 amps, but what about this one? Okay, well, what we want to realize here is that you always sort of pick the diagram that's like going to be the easiest to work with. The easiest one to work with that allows us to see this current here is going to be this diagram here. This one here is more complicated looking. This one here is simple enough while still having the thing we want in it. So the way we're going to look at this is we're going to realize that electrons here have 36 volts. Electrons here have 0. They don't lose any energy in wires. So that means electrons here have 36 volts and electrons here have 0 volts, and ditto over here. So that means we've lost 36 volts in a 1000 ohm resistor, which means we have a certain amount of current that we can use V equals IR on. So A2 is going to be this current through here, and it's going to be, sorry, that bit of sunlight makes it kind of hard to read, 36 volts divided by 1000 ohms equals 0.036 amps. And if we wanted to know how much is going through the other one, we've got two options. We could say it's 36 volts divided by 800 ohms and get some value. Or we could say, wait a minute, 0.036 through this one, 0.081 is the total, so this just must be whatever's left over. So either way, you can find that. You could reverse that logic, by the way, and you could just use that separately to find each of these, add them together to find that. So we could have done it the other way around if we wanted to. And then the last step is we want to find the voltage across that 600 ohm resistor. And we notice that, well, that's kind of in here somewhere. So this diagram is not the appropriate one to analyze this. So we need to step out again, right, and go back to our original diagram. But now we know a little bit more than what we knew before. We know that this is 0.081 amps, and we know that this one here is 0.036 amps. And we're just going to look at V2 here. And we say, well, how much current is actually going through that resistor? Well, it's not A1, it's A2. It's that there. So how much current is going through that? 0.036. It's got 600 ohms. If we know the current going through a resistor and we know its resistance, then we know what voltage drop is going to be across it. So it's going to be equal to IR for that resistor. So it's going to be 0.036 amps multiplied by 600 ohms equals, where have I got it written? Somewhere. 21.6 volts. Okay, just as a little mental check at that point, it should always be some sort of reasonable fraction of whatever you started with. So if we'd got like 60 volts here, we'd say, wait a minute, the electrons only have 36 volts. So how can they drop 60 just in that resistor? On the other hand, if we'd got like 0.1 or something, you'd say, well, there's a 600 ohm resistor here, there's a 400 ohm resistor here. Is it really reasonable that as the electrons go through this path, they only drop 0.1 here and they drop all the rest in here? Not really. Okay. So you can you should be able to do a few mental checks when you're doing these problems. Okay. Last one. So this one is quite complicated and it's going to take quite a few little redraws as we go along. So let me just find a nice bit of blank paper to work with. Very quickly filling up my sketchbook here. Okay, so So I want to take that diagram there and I want to simplify it. So the way we do this is we're always looking for things that are the most simply connected. So first off, we look for resistors that are just right next to each other and that we can just treat as a series, just add them together. But I can't see any like that here. I can't see any like that here because you might think, oh, this 4 and this 5 are next to each other, but before the 4 gets to the 5, we split off. And before the 5 gets to the 10, we have another split off. So there's nothing that's really straightforwardly connected in series. So the next thing we're looking for are there resistors that are kind of doing the same job that get you from A to B, but by parallel paths. And when we look at that, we see that getting from here to here, there's 2 parallel paths straight across that one or straight across that one. So those are doing the same job of getting from A to B and nothing complicated going on. So we're going to take those, and those are the ones we're going to treat as our equivalent resistors. So that's going to be our first simplification, is we're going to take those 2 and turn that into an effective resistor for those 2 10 ohm ones. And the rest of our circuit is going to be unchanged. So that's going to be our 5 ohm there.
Mr. Malone.
Yes.
I sent you my answers. Can you just check?
I'll have a quick look at them.
Thanks.
Hold on one sec. Pause video here. 3. They're not exactly what I get. So maybe just check when or maybe hang around, or if you want to leave, then have a look at the video. But yeah, they're not exactly what I get. But you never know. You could actually be right and I could be wrong. Let's see how this shakes out. Okay. All right. So we've got this effective resistor here. Let's just finish off the circuit. Forgot to do that one there. And we have 5, 40, and 4 here. Okay, so we need to work out what is this effective resistance that's doing the job of these 2 10s. Now, it turns out that if you have 2 resistors in parallel that are identical, you're actually just going to double the amount of, you're just going to halve the resistance or double the current through them. So this RF is going to be, you can work through the formula, but trust me for now, that RF there is going to be 5 ohms. Feel free to pause and go through that. Okay, so now we just do the same thing again. We're looking for things that are close to each other, either in series or in parallel in a simple way. And we look at this and we go, oh, wait a minute, these 2 are right next to each other with nothing else complicated going on. So we can simplify those guys down to a simpler circuit. So we're just going to take those 2 and they're going to be our new effective resistance we're looking for. And then those together are going to be in parallel to our these 2, and we're going to have 40 and 4 and 24 volts. Didn't put it on before, 24 volts. And we need to know what this R effective is. And this is just 2 5s in series with each other. So the effective resistance there is going to be 10 ohms. All right, hopefully we're starting to get the picture. Now, we're looking again. Have we got anything in series? No, because the 4 and the 40 might be in series, but they've got this other bit coming off before they connect. So we're going to have to look for parallel things. So here it is. Here's our parallel. So let's redraw. These two become our effective here. And the rest of our circuit is just that 4 now. We got 24 volts, 4 ohms. Okay, now this is one I can't do in my head because I've got a 10 and a 40 and they're not obviously connected together in a simple way. So we better do the actual equation here. RF equals 1 over 10 ohms plus 1 over 40 ohms. I'm going to take out 1 over 10 ohms as a factor. So I get 1 plus a quarter. So 1 over 10 ohms outside of 5/4. Then I'm going to flip them. And we get 10 ohms times 4/5. So that's 8 ohms. So the effective resistance of this guy here is 8 ohms. And I suppose I could do one last redraw, but it's pretty obvious what's happening here. We've got an 8 ohm and a 4 ohm. So the total resistance here is 12 ohms, which means the total current we're getting is, lordy lord, 2 amps. So I can't remember whether that was A1 or A2 or whatever it might be, but we're getting 2 amps out of the battery there. Okay, now we just work our way back up the series to work out everything else we might want to know. So let's just go back to our original diagram to check what it is we want to know and whether we can mark it on these diagrams. So we would like to know A1. Yep, that's what we found. That's the total current. That's going to be that 2 amps there. We would like to know the A2 and A3, which in our diagrams here are going to be, that one there is A2. A3 is actually hiding inside that resistor there. That got crunched away when we joined up these two paths. A2 is still here because when we added these two resistors, we didn't get rid of that one there. And the voltage across that 5 ohm, yep, that's still here, V2. But by the time we get to here, it's gone. So I'm just going to close those curtains. Okay, so we're always going to analyze our circuits at the sort of the lowest level where it's easier to do so. So if we want to look for current 2, then we can't use this diagram here because it's been crunched away in the effective, but we don't want to use this one either because this is more going to be more complicated. So we want to use the simplest one we can. Okay, so we look at this and we say, wait a minute, there's 24 volts. There's 2 amps moving through this whole circuit here, but that 2 amps gets split up this way and this way. So it's only some fraction of them that goes through. Now, if you're confident using ratios, you can say, wait a minute, I've got 2 amps and it's going to get split up, and the ratio of the way it gets split up better be 10 to 40, 40 to 4 to 1. All right, so it's going to be, if you sort of quickly do that in your head, it's going to be 16:4 or 1.6 to 0.4 is going to be that ratio. So it's going to split up 1.6 amps to 0.4 amps. Okay, and then you say, well, which way around is it going to be? Well, the 1.6 is going to go through the low resistance path, and the 0.4 is going to go through the high resistance path. So it's going to be 1.6 amps through the 10 ohms and 0.4 through the 40 ohms. Okay, now you might say, well, what if I just can't see that ratio? Or what if the numbers are really ugly? So let's actually work through it a little bit more systematically. The key to work it out is, well, we would normally in a parallel circuit, we would normally say, we'd take this 24 volts and we'd say that 24 volts is getting dropped across a 10 ohm resistor, divide through by 10 and we get 2.4. But notice that some of that 24 volts is getting dropped on this 4 ohm. Right, so we're not going to get that full 24 volts over here on this resistor. So that 24 volts, we've got to work out how much of it is getting lost on this 4 ohm one first. Well, that's fairly easy, we know, because we've got 2 amps going through it. It's a 4 ohm resistor, so that means it is getting 8 volts. Right, so if it's losing 8 volts, then that means we've still got 16 volts left when we get to this junction here. But when we get over here, we're going to have 0 left. So that means 16 volts gets dropped in that 10 ohm resistor. That means the current through it must be 1.6 amps. Okay, so first we worked out how much was lost on this bit here. And then we said all the leftover must be getting dropped between here and here. And we've only got one resistor in the way, so we can use Ohm's law. So V equals 16 volts, I equals 16 volts divided by 10 ohms equals 1.6 amps. And you could do the same thing to find the current through this 40 ohm. You've got 16 volts divided by 40 ohms. You're going to get 0.4 amps. Yeah. Cool. All right. So we've now found A2. A2 is going to be 1.6 amps. Okay, we're slowly getting there. We work backwards, 1.6 amps, and we say, okay, wait a minute. I've got 1.6 amps going through this whole branch here, and we've got 16 volts being lost across this whole branch here. But not all of that 16 volts goes into that 5 ohm. But it's pretty simple to see if this is 5 ohms and this is 5 ohms, then how much is going to get dropped? If it's 16 volts total, it's going to be 8 into each of them because they're the same. But let's say we can't see that straight away. It's sort of, electrical circuits are always kind of a combination of what you can sort of just intuit and versus what you have to sort of work out more systematically. Well, let's do it systematically. We've got 1.6 amps going through. We have, that's going through this resistor here because they're in series. We've got 5 ohms. So the voltage drop at V2 is going to be 5 ohms multiplied by 1.6 amps is equal to 8 volts. So we're going to have 8 volts on that V2. Okay, so finally we can go back to this page and we can actually just write down all our answers. So we had that A1 was written on here somewhere, 2.0 amps. We had that A2 was 1.6 amps. We had that did we even work out A3?
No, not yet.
Oh no. Oh, shivers. Okay. All right, we still need to work out A3. We had that V2 was 8 volts, and we still need to work out what A3 is. Okay, well, our simplified diagrams aren't going to do us any good because A3 is inside that simplified part. Okay, well, let's think about what's going on here. A3 is the current that's just going through this one resistor down here. Now let's think about the current moving through this circuit. We worked out before that it's already lost 8 volts on here. It then loses a further 8 volts on here. So by the time it gets to here, it's only got 8 volts left. From here, it's got a clean path back to the negative terminal. That means it's got 0 volts left. Okay, if it's got 8 here and 0 here, it must have dropped it in here. So we can use V equals IR, 8 volts, 10 ohms, 0.8 amps. Okay, now we'll give you plenty of practice at those sorts of questions. That's about as hard as they get. Over the next week or so, you're going to get really good at these, and then by the end of the week, you're going to be able to do any one I give you. Okay.
I've just got a question.
Yeah, okay.
Let's say if we placed a amp thingy right here,
Mm-hmm.
right? Would that be the difference of A2 plus A3?
Yes.
Yeah, okay.
And then this one here, if we put one here, it would be the difference between A2 and A1.
Yeah, okay, cool.
Yeah. So notice that A1 is the biggest because it's the overall current. And then every time you go down to a smaller level, you're splitting off some.
Yeah.
But not always evenly.